We've pretty much done everything we need to look at for initial value problems. Theoretically, although not covered in great detail and not going to be assessed in great detail, you can have any kind of initial value problem, any order, like say in structural engineering, there's fourth order differential equations and initial conditions. You can go off and solve it, but there's actually a load of things that you can't solve. Okay. So let's look at a first order initial, all first order differential equations are initial value problems. So you have the derivative given in terms of x and y and an initial value of the y variable at some particular point. So by their very nature, either mathematically or in context, a first order differential equation has infinitely many solutions. So for example, consider a Newton cooling. Now here k is some unspecified constant and T0 or Tr is a reservoir temperature. Now I just have to be careful, just have we got the signs right here. So think about the reservoir maybe as the room temperature for a cup of tea, and say T of T, the temperature of the tea. I know there's a lot of T's going on there. Big T of T is the temperature of the tea. So if the tea is hot, then T of T minus Tr is positive. But when the tea is hot, I want to see that the rate of change of the temperature of the tea is negative. And indeed, that's why I have the minus k. If I write Tr minus temperature at time t, there will be a plus k at the front. But this is correct. Now, we have different initial temperatures, and each one has a solution. So there's infinitely many different initial conditions, and each of them give you a slightly different solution. Okay, so I think we could probably write down the solution. You could probably solve that exactly using stuff you know from Marina's class. Similarly, free falling with linear drag. So this looks like, now I'm just gonna, a bit lazy here, I'm gonna go mass times acceleration. Oh no, I'm not. I'm gonna do, let's do m dv dt, mass times acceleration is equal to, now we're gonna pick down to be positive here, both for x and v. So gravity goes down, and linear drag means it'll be, say, a constant times v. And then we've got some initial velocity v0 as a solution for every possible initial velocity. Okay, to narrow down from this infinity of solutions, we have to specify the initial conditions. So what I'm trying to say here, it probably wasn't well said, is that this has infinitely many solutions. This has infinitely many solutions, but if you want to narrow down from the infinitely many solutions to the unique solution, you give an initial condition. That's probably what I want to say. So this is similar to in differential equations. Say you're doing undetermined coefficients and you got an a and a b. So there's infinitely many solutions there, but if you can specify some initial conditions, you can find that a and that b. And usually in Laplace, there'll be initial Laplace transforms, there will be initial conditions given. So narrow down from this infinity of solutions in yellow, we have to specify the initial conditions in orange. We have to specify the initial temperature or the initial velocity, for example. Mathematically, the solution of a first order differential equation, like if you think about solving any of these yellow things, there's going to be somewhere an anti-differentiation. So there's going to be a constant of integration. You need only one value of the output for a given input to write an equation and see which you can solve. So in a first order, one initial condition, you can narrow down from the infinity solutions, but it's kind of singly infinite. There's only one constant of integration down to the other one. I can also think about this kind of dynamically. So, say we have an initial point on the curve given by x0, y0. Then what the differential equation essentially does is it tells the curve which way to go. Because look at what the differential equation does, it tells you what the slope is. So if you go down here, you say, okay, the differential equation says go this way. Now, of course, it's kind of a bit more complicated than that, because you know, Euler's method says change direction every step h, but this is continuously changing direction. So it's not really a straight line there. So it's kind of continuously changing direction, telling you where to go at each instant, giving the slope of the tangent. That's what the differential equation does essentially. Okay, so so suppose this is continuously changing. The differential equation, the ordinary differential equation, gives slope at xy, and essentially, so you kind of dynamically, so once you know the differential equation tells you where to go essentially. Okay, right, that's okay. Now consider a second order differential equation. So a second order differential equation, we could write this down as it would be the second derivative is given in terms of the first derivative, excuse me, x, y, and the first derivative. Now we know that we can, now I'm going to write something here that we need to understand that we can do, that we can split this into two first orders. So we can split it into a dv dt is equal to, so this will be something, I think it's basically just a change of variable, so I can just keep the g here, x, y, v, and then the other one is dy. You know, I've got a mixture here of y's and x's. Now normally I would kind of stay on the t's, but here we want to kind of go to x's actually. So the other one is just dy dx equal to v. So yeah. So, but just for the moment, think of a second order differential equation. So the purposes of our discussion, we can consider the real pendulum, which looks something like this. So this one has a doubly infinite family of solutions. So if you give just the initial angular displacement, so if you give the value of theta at time equal to 0, it's not enough to narrow down to a single solution. You might also need to know the initial angular velocity. So think of a pendulum. There it is. And if you know the initial position, so that'll be a negative angle here, I suppose, the way this is set up. That's not enough to know because, well, there's all different initial angular displacements. It could be released from rest. It could be given a negative that'd be kind of going up and then a positive going down. So you must also know the initial angular velocity. Same mathematical reasoning as above. Second order differential equation should have two anti-differentiations, and so somewhere two constant integration. So if you've got two unknowns, you need two equations to narrow it down. And so if you give, say with the pendulum equation, the initial angle and the initial angular velocity, then you have two equations, two unknowns, and you have a unique solution. You can also think of this in the geometric way. Now perhaps this is a little bit harder. I'll give it a go. This might be Gallus. So we've got the initial slope. Now the differential equation tells us what's going on with the second derivative. Now what that means is, i.e., so if the first derivative is the slope, is how y changes, the second derivative is how the slope changes. How slope changes. So we have an initial slope that's actually given in the initial conditions there. So we know that. But then the differential equation says what's happening with the slope. So if the slope, if the second derivative is positive, it means that the slope is getting bigger. If the second derivative goes negative, that means the slope gets smaller, it goes from positive maybe to 0 to negative. And then kind of this helps you understand stuff about the shape of the graph in terms of second derivative. So here slope is negative. Maybe we'll zoom in and write down some things. So here, bad choice of color. So at this point, y dashed is positive. At this point, y dashed is negative. And back here, excuse me, up the top, y dashed is not negative, it's 0. And down here, the slope is negative. So what you have here is the slope has gone from positive to 0 to negative. So the second derivative is negative, because the second derivative is the rate of change of the slope. And so if the slope is going from positive to 0 to negative, the slope is decreasing. So the rate of change of the slope is negative. That is, the second derivative is negative. And then you can kind of get bits where, say the slope doesn't change at all, then the curve looks like a line. So this is places where the second derivative is close to 0. The slope does not change. And then say at the moment the slope is negative, suppose it starts increasing to 0 and up to positive. Well, that's second derivative being positive. So this is stuff about second derivatives and shapes of graphs that you should know about. If kind of a bit lame now, but if the second derivative is negative, you got to frown. If the second derivative is positive, you got to smile. Look, it's a bit callous and sad, but it works. The piece about needing two equations suggests another approach. So we just said up here, if you want to find the two constants, you need two equations. Okay, so there's a different way that could happen. So suppose you have a second order system. So we can write that as the second derivative is given in terms of x, y, and dy dx. So all we need to do is generate two equations, really. So what we could do is maybe if we knew the value of y at two different places, say at x1 it's equal to y1, and at x2 it's equal to y2. So then in theory you have two equations and two unknowns which can be solved. So if you have a second order differential equation, normally you say, oh, you want two initial conditions. That's what you know from Laplace. I mean, if we write down a little bit from Laplace, what does Laplace say? Laplace says that the Laplace transform of the second derivative is s squared times the Laplace transform of the function minus s times the initial value of the function minus, and I might have a sign error somewhere, maybe not. The initial, so Laplace is for initial value problems. So see the way you're looking for information at the same point. So this says that so Laplace is for, in general, initial value problems. Now it can do more. So this thing down here is a bit different. So this is usually what we're going to call a boundary value problem. So you've got your x values, and rather than specifying what's happening at the start, say at x equals 0, you're saying what's happening at the start and at the end, and these would be your boundaries. So really you're only interested in what's happening in between those 2 points. So x1 and x2 would be the boundary. And you can write down some fancy notation for boundary, but we don't need that. Okay, so second order differential equation, you can specify two boundary conditions. Now if you have a first order differential equation, you can't guarantee that you can specify the two of them. In general, you won't. So you can say like, oh, here's my cup of tea. You can say the initial temperature is whatever, 100. But you can't say after 10 minutes, I want the temperature to be 20. You don't control that without maybe changing the design of your cup or whatever. Okay, in context, this doesn't make great sense. So for example, the pendulum equation, if I can remember how to write it down. So the second derivative of the angle is it minus g over L? It's a bit pathetic, I have to go back. Oh no, not too bad. Minus g over the length of the pendulum sine of the angular displacement. So I think what we're going to do is we're going to get, so this would be, say at the start, say t0, we say that the angle is t to 0, and after a certain period of time, we say that the angle is t to 1. That's not very natural. So you have a cup of tea, you can't say, oh, it's 100 degrees, in 5 minutes I want it to be 20. You don't control that. And to an extent, it feels like that with the pendulum, with this. You say, oh, here's the starting angle, and after t1 seconds, or should I say t1 minus t0 seconds, I want the angle to be this. You can't, without thinking, and we'll talk about that in a second, you can't do that. But actually, this can happen. So for example, suppose you want the initial angle to be pi over 2. So this is y equal to theta of t, x is equal to t, or just t. So this is the initial point, 0 pi over 2. And then after 1 second, I want displacement to be 0. So the story is, like, how can you make that happen? Think about it. So just think about, you have a pendulum in front of you. It's initially at 90 degrees. And after 1 second, so here's t equal to 0, and here's t equal to 1. How can you make that happen? So have a think about it. Have a think about it. So the first thing you'd probably do is you'd let go. And say you let go. So we'll write that down. So if you let go, that's saying that the angular frequency, that's the derivative of the angular displacement, is equal to 0. And maybe after, let's say, 0.2 of a second, the pendulum falls. So it falls in 0.2 of a second. Well, what would you have to do then? Well, you'd have to give it some initial velocity. Positive, well, actually, would that be negative? No, yeah, positive. The writing there isn't great by me, apologies. So what I'm saying is you want the pendulum to close in 1 second. Now omega here, maybe I just need to be absolutely clear about something. So you can use v to be defined as the first derivative of this. That would help you write down the second order differential equation as 2 first orders. Or actually, see, normally v is like the derivative of the displacement is the velocity, and that's fine. But in this context, the derivative of the angular displacement is something called the angular velocity. So instead of using v, you could use omega. It doesn't really matter. They're the same thing. Okay. Well, sorry, velocity and angular velocity are not the same thing, but in terms of, in this question, if you use the symbol v or the symbol omega, it's the same thing. The v would not be the velocity, it would be the angular velocity. Okay, well anyway, so you let go of this pendulum, it's at 90 degrees, it closes in about 0.2 seconds. Maybe we should say this is just approximate. So it's around the 0.2 seconds. And so that won't work. So what you have to do is instead push the pendulum up, give it an initial velocity, and for some certain value of the initial velocity, it will close in 1 second. So saying that you want this to happen does actually determine something. It determines the initial velocity. So omega 0 is determined by the two initial conditions, theta of 0 is equal to pi over 2 and theta of 1 is equal to 0. So you get your solution maybe like that. I don't know exactly what it looks like. Whereas if you did just, and if you just let go, it closes in 0.2 seconds approximately. That's what we're saying. Okay. So hopefully that makes some kind of sense to you with the picture on the right hand side. So this though isn't very natural. So the pendulum isn't set up to be what's called a boundary value problem. It's far more natural for it to be an initial value problem. Okay, so, but there are different problems that are like this. So for an example, if you think about what's called a simply supported beam. So you got one support that's fixed and another support that's on a roller. Doesn't matter, hopefully drawing the thing between these. All right, now we're going to have a load on it, but I won't actually show the beam deflecting. Go on. Oh, nice. Sorry, I'm just trying to draw a picture and I'm not very good at it, so. Go on. All right, so, and I got loads on it. Now, so we've got loads. Now you got the load per unit length at each point. Okay, it can be shown that the relationship between the load per unit length x, so where's x coming in here? So this is x equal to 0. and then you've got the distance along the beam. So this, the x-axis is actually kind of slightly deformed. It's basically the x-axis, and then this is x equal to L. Right, so it can be shown that the relationship between the load per unit length, so that's basically saying the intensity of the load. If the load kind of went constant for a while over 1 meter, how many kilonewtons would it be? And the bending moment, which I'm not going to explain fully because I don't fully understand it in many ways, is that the second derivative, okay, I'm going to use plus here, but it should be negative really, is equal to plus W of x. Okay, now if the beam is simply supported, then what we have is two conditions. So here, like, remember we said it down here that if you have a boundary value problem, you're only interested in the value between 2 points, basically. Now it can be more general than between 2 points, because it could be in 2 dimensions, it could be on a square, but there is a boundary, which is the point x1 and x2, or the points x1 and x2. Like, I'll just write something fancy. So say the region would be what you're interested in. So the region would be, you're interested in all the points from 0 to L. And then the fancy bit would be, what's the boundary of the region? It's the point 0 and the point L. Oh no, oh, there it is. Okay, that's just the fancy thing I wanted to do. So that's why it's called a boundary value problem. Right, so strictly speaking, the sign should be minus. Okay, now, so what we're saying is that there are two conditions that need to hold here. And now you can refer to what you learned before about bending moments and stuff, but the bending moment that is as a support, if it's simply supported, is 0. So the bending moment at 0 there is 0, and the bending moment at L is also 0. So what you have is, there's two things that are specified here. That goes there, that goes there, and then what are you looking at? Well, you're looking at what happens in between. Maybe it goes like that for argument's sake. Okay. So if the beam is simply supported, then we want to say that M of 0 and M of L are both equal to 0. And this is boundary condition. So this is a boundary value problem. And this is where this is natural. It's not so natural for the pendulum. Now, if you want to kind of look at kind of designing things, so like designing a pendulum, you can kind of talk about it as a boundary value problem, and that's okay. So say, for example, you wanted the pendulum to close in 1 second. Then you would solve this by, I don't know, is it quite a goal seek? It could be a goal, it would be hard to do goal seek. I don't know how the goal seek interacts with the VBA, but anyway, so what you'd be doing is you would be enforcing the boundary conditions, and that would determine the velocity. So the design would be, find the initial velocity such that the pendulum closes in 1 second. It's far more natural here. There's just kind of one answer, right? So let's look. So for example, for a beam of length L equal to 5 under a constant load. Now here you see it's plotted upside down, but I could plot it either way. Don't worry about that. Okay, another context when it makes more sense to specify boundary conditions rather than initial conditions is when looking at the heat in a log. So it says here it's uninsulated. Yeah, that's true. So you have kind of a wall here and another wall here. Now they don't have to be walls, they're just some kind of components of some sort. And you have a rod going between the two of them. Now it's uninsulated, so there's different heat transfer. So the temperatures at the sides is kept constant. So temperature here be temperature 1, and temperature here be temperature 2, and you also have the temperature of the air. Whereas our x-axis is basically the same as the rod. So if I just draw this there, this is x equal to 0, and then this is the x-axis, the rod is the x-axis, and it goes up to x equal to the length of the rod. And then the initial conditions are given by T1, which is the temperature at the start and T2, which is the temperature at the end. And you want to say, what is the equilibrium temperature here? So if the rod is not insulated along its length and the system is in equilibrium, the equation that governs the temperature at a distance x along the rod is given by this. We may or may not see that equation a bit later on. So H dash is a heat transfer coefficient related to how much heat is being given off here. I think I can draw a cool kind of picture. Of course, the heat can be going into the rod or out of the rod. So this is kind of proportional to H dash. Well, that's not right. So H dash is the constant of proportionality. And obviously, like you get a heat transfer, like you'll get it going this way if the temperature at the point X, say, is bigger than the air temperature, whereas you'll get heat going into the rod if the temperature of the air is bigger than the temperature of the rod at that point. Okay. So, and then the H dash is the constant of proportionality. So the difference between those, the temperature of the rod and the temperature of the air, the bigger that is, the more heat transfer you're going to get. And the constant of proportionality, which kind of says how good is the air and the rod at kind of transferring heat, is H dash. And then the other term is something to do with equilibrium, which we should see later on. So we'll see, for example, an L equal to 10 meter rod with TA is 20, that's the air temperature. Temperature on the left is 40, temperature on the right is 200, and the H dash equal to 0.01, the method of undetermined coefficients. Can Laplace be used here as well? Not very well. But anyway, undetermined coefficients can be used, that this is the solution. And so here you see, so at 0, the temperature is at 40, and at 10, the temperature is 200. Now see the way you have a little bit of a dip there? That's because the air temperature is 20, so it's cooling it. If H dashed is bigger, the dip is more pronounced, if you know what I mean. Temperature would be, the rod will be colder, okay? But you're still going to have at 0 along the beam, the temperature is 40, and at 10 along the beam, the temperature is 200. So this is another example of a boundary value problem. So I think in the next one, we're going to look at something called a shooting method, so a method for attacking these.